Our next speaker is Wayne from Tailings, and he'll be giving a talk on passive seismic measurements for extended continuous pore pressure monitoring of tailings dams.
Forward, back. There we go. Good morning, everyone. Thanks to Saga for the opportunity and to all who are attending. I'm presenting on behalf of my colleagues at Geophys and SRK. We've been working the past year on this project, and most of what I've learned about tailings, I've learned from my SRK colleagues. And Adrian, thank you very much for setting the stage at just the right level. You're going to hear from James shortly. Lindsay, who's given us so much help along the way. Passive seismic measurements for extended continuous pore pressure monitoring of tailings dams. Same problem. Oh. Still nothing. Here we go. A brief outline. I'll answer the question why we did this work, and look at the method and the results of a pilot project that we did. If time allows, we'll look at some other parameters that we can extract from the same data set, and I'll wrap it up with a summary of key points. So why consider passive seismics to monitor tailings? Well, I think the challenge was laid down by Adrian there. We need more instruments, we need better measurement, better prediction of where things are going wrong in a structure. And here we have on a mine site a free source of energy in the ground. In passive seismics, normally we'd like to get rid of that noise in a seismic survey, but here, one man's trash is our treasure. We've got sound waves moving through the ground, bringing information to our sensors, and we're measuring surface waves in this case, which are dispersive and allow us to plumb different depths for information by looking at different frequencies. Yeah, one of the strengths of this particular method is its complementarity with what's already being done. So we're not wanting to replace, at least not in full, what's already being done in terms of monitoring. And also, we'll talk more about the interoperability. It lends itself to that. Yeah, again, this is not wanting to advance. There we go. Some other benefits are that it's a non-invasive method. It's basically superficial equipment and allows for a flexible deployment and a rapid deployment. It provides volumetric information, which is something different to what's done. Everything else is point measurements and limited to specific depths. We can provide a full coverage of the structure. And we have access to the internal structure of the structure with the depth discrimination. So it offers a continuous monitoring tool that is actually highly sensitive, as we'll see, to the very things that we want to track. So we are proposing that this will enhance structural health monitoring on tailings facilities and others, structures. But in two main areas, we can track seismic velocity changes with ANI, an acronym, which is ambient noise interferometry. It's a well-known method of processing the data to extract from the noise a coherent signal. If you want to know more about it, you're not going to hear here. You'll have to go and look it up. There's not enough time. And with this, we will show how we can monitor pore pressure changes. All right, and the other area of information, which I hope I can get to briefly, is that we can extract from the same data set certain geotechnical parameters like resonance frequencies and damping ratios. I suppose I can get rid of these. Sorry. I forget that they're there. So we did a pilot project over 5.5 months here of monitoring 33 geophones, 3-component geophones for 4.5 hertz installed on the facility. And 2 of them were co-located with VWPs. This was a well-instrumented facility. And those are shown by the orange circles there, those 2 sites. So we were able to compare results with established measurements. And along the way, we were guided by the geotechnical engineers because we were new to tailings, and by Lindsay in terms of the geophysics. You saw from her talk. She knows what she's talking about. And we validated the results with the engineers as well, which gives us some personal level of comfort in what we're offering. So here's what we do with the data. This is a 3D velocity model, shear wave velocities, within the polygon shown on the thumbnail there. And there are 3 main features to observe in it. The red zone, the upper zone, and then the blue zone, which is the deeper zone, and the interface between. The red zone, we correlate with the capillary zone, where natural consolidation and desiccation is taking place. And the blue zone is below the phreatic surface, where it's saturated and where pore pressure effects are predominating. The interface between them is our estimate of the phreatic surface level. So this gives you good visibility, subsurface visibility of your structure. And then we can iterate this model and provide a 4D seismic velocity model tracking velocity changes through time and spatially. All right, so here's a sample of the data that we collected. There's a lot more than this. The 2 sites where our sensors and the piezometers were co-located. The blue curves here are the data from the geophones, and the green curves are from the piezometers. And the curves are smoothed so that you can see more easily the correlations and the trends that are significant. If you look at the vertical scales, the velocity changes, which are in percent, that full scale is about 1.5%, and the pressure scales about 1.5 kilopascals in the full range. So these are very small changes. They're not what anyone will lose sleep over. You're happy to see this. But it does allow us to determine that we have a sensitivity of about 0.2% change in velocity, shear wave velocity, which in this facility corresponds to a pore pressure change of about 0.2 kilopascals. And that in turn is related to about a 2 centimeter level change in the phreatic surface. So this is quite a sensitive tool. And the correlation coefficients you see there are very pleasing. They're around 0.8, which is pretty good. So we're saying that this tool can be used as a pore pressure monitoring tool by tracking the relative VS change. So if we apply it to that pore pressure monitoring application, we can provide hydrogeological information between boreholes, between these 2 piezometers here. It's about 300 meters, I think. And it allows us we have more instruments on the dam, and allows us to cross-validate results from 2 independent measurements, gives us some redundancy in the equipment because equipment fails, and we can reduce false alarms with this layer of information. So we see the method allowing a monitoring of depositional cycles, the influence, so you can see whether you're doing it too fast or too slow. We can track the effects of meteorological events and seasonal changes, and also construction activities. So if you're going to put in a a buttress, you're going to put in a shear key somewhere. We could monitor the impact those activities have on the dam during the construction phase. So one of the advantages is the interoperability, because really it's a simple time series. We generate the models, we do inversions, but the underlying raw data are these time series of velocity change, which are pretty easy to push into any dashboard database environment. This is a real case that's demonstrated here, where we have, you know, our curves against VWP pressure curves. These are all our curves from all the stations, I think, pushed into a live monitoring platform. So that integration into the client data environment is quite easy to implement, and integrating it into a TARP structure is more of a challenge, and that's something we haven't yet got to, but we will, but only in collaboration with the engineer of record, and to do it in a responsible fashion. The equipment looks like this. Top right picture, it's a digitizer in this gray box. Actually, there's 3 in there, and a cellular data modem, an external battery, lead acid battery, which is charged by a nice big solar panel. That thing will just keep running by itself. This one, I think, is a microseismic station. There's only one cable going in there, but we have 27 channels in our version, so we can support 9 3-channel sensors with it, which, depending on the station spacing you pick, but we can cover about 1 kilometer along a wall with one of those. And that thing is hooked on the internet through the LTE data, 4G data service. These recorders, you know, they're robust. They've been out there for some years, and they have a mean time before failure of 2 to 3 years from the track record. So it's minimal site intervention. And obviously we can, through the internet, directly access the instrument. We're looking at, you know, raw stream data samples here, all the parameters for the digitizers, and the lower right, which I might be in the way for some of you, but it's an example of the Nagios diagnostics platform, which we use to in real time monitor the health of our instruments, and that can be configured with alerts and can send SMS, email to the designated person to respond immediately to any problem. So the data logger can be monitored and configured remotely. It collects and stores data to a high resolution, up to 2,000 samples per second. We don't use it for monitoring at that level. We typically stream data at 100 or 200 hertz to the cloud, and that's using Amazon Web Services. It's what do you call it? Sorry, the word escaped me, but it's a secure transfer, and we're currently sending 2-minute segments encrypted. Here we go. All right, so we have a processing that's pretty much automated, and the data, once it hits the processing server, will give you results in 2 hours, within 2 hours. And we can make those calculations hourly or daily in terms of time steps. Typically, we like to do it daily because the geophysics listening longer allows you to stack data and give you a more stable signal to work with. 2 minutes. All right, so I've got 2 minutes to look at these parameters. The resonance frequencies we can extract from the data using the HVSR approach, horizontal vertical spectral ratio. I think that's well understood, and these numbers are realistic. I think Adrian would agree. You'll see most of them are higher than about 2 hertz, and I think 2 hertz is typically used as a resonance frequency for this type of facility anyway. So the damping ratios, which we computed here for those resonance frequencies, because they can be computed for any frequency, are also variable across the structure. And I don't, that helps us with the seismic risk predictive modeling, because those numbers are put into predictive models. And then we can assess any microseismic events with the data that we collect. This is an example of a blast from a nearby pit. And we can characterize with that the frequency ranges and amplitudes in that particular blast, and you can see it gets pretty close to those resonance frequencies on the dam, and if not, the same as some of those values. But with this sort of a plot, this is 1 minute of data. It allows us to see the pre-excitation state and the relaxation back to that background state, and some idea of the residual seismic energy, how long it persists, or how quickly it attenuates. And that allows us to do an ongoing assessment also of the impact of blasting on the structure itself directly. So yeah, let me finish. Key messages. The passive seismic dataset can be multi-purposed and provide multiple levels of information, both in the monitoring and extracting of geotechnical parameters. Monitoring pore pressure variations over the full depth profile into the foundation, if we have the frequencies to allow that, and we can do it across the entire structure with high sensitivity. And it provides easy interoperability with existing platforms and the cross-validation of the values measured by independent methods, and it can be integrated into a top and surveillance platform. It's a non-invasive method, it's easy to deploy, and it's adaptable through the life of the tailings facility. Thank you very much.
Thanks, Wayne. I think we have time for one quick question. Paul, Wayne. Glenn?
Glenn. Oh.
Very nice presentation. Just one question. I work with a number of mining companies, and much of their complaint is on the cadence of processing. Is this something that can be done on site by site personnel, or it needs a specialized personnel?
No, I don't think it can be done on site. We're sending large volumes of data to a cloud server and processing it with proprietary codes in an automated workflow. Unless a miner is willing to invest in high power computing and pay a license for that, and unless the company is willing to license that workflow, I don't think it will happen. And there would have to be a subscription to a monitoring service. Jeff. Oh, beg your pardon.
I just want to ask, are there any environmental geological conditions that impact this measurement, and how do you overcome these to stop this interference?
There are. I mean, pore pressure change is not the only factor that will affect the shear wave velocities. So it's just the predominant factor. And it is definitely the predominant factor in the saturated zone. So you can't just assume that the higher your facility, the better the compaction at depth, the more stable it will be. It's probably sludgy down there, and looking at these pore pressures. So yeah, there are other factors that one has to consider, but we've got the empirical evidence of that correlation, and we're also working on actually the analytical solution to that. So some of that will be answered by the physics and the maths eventually.
Awesome. We could do one more quick question.
Wayne, you appear to lay out a profile of 3-component geophones there. If so, what was the separation between them?
Yeah, in this case, it was variable. It was between 40 meters up to probably 100 meters. You would tailor that to your specific requirement.
Yeah.
But what we have established is that we can achieve the sensitivity that we need up to 100-meter spacing. And with that, we can cover with one record 1 kilometer distance along a wall and know that we're covering the full volume.
So that 100-meter may equate to the spatial resolution of the seismic waves that you're mapping?
Yeah, that's a good question, but that's not really an issue because it's what I like about this method, Jeff. We don't need high frequency data to measure very subtle changes in velocity. You can do that with the longer waves, and you can do it with high sensitivity and with good repeatability.
Okay, thank you. Well said.
Yeah.
Awesome. Thanks, Wayne.
Yeah, thank you.